Hello, this is Jack Jackson. Today we're going to be looking at graphing exponential functions and logarithmic functions graphed by sliders. And I pulled up this GeoGebra investigation, okay, and in this we're able to manipulate the parameters c, k, and a. And we're looking at, if you look over here, you can see a function that's going to be in blue that's an exponential function, and right now the value of k is about 0.69, and so that gives a b of approximately 2, c of 1, and a of 0, and then r then turns out to be 1. We'll talk about those things in just a minute, but the basic form is y equals a plus c times e to the k, let me say that again, y equals a plus c times e to the power kx. And it turns out the inverse function of that is 1 over k times the natural logarithm of x minus a over c equals y. And let me actually just derive that for you here. Okay. And so we've got our formula, our original formula, okay, is y equals a plus c times e to the power kx. Now when we go to the inverse relation, we switch x and y. So the y becomes x and the x becomes a y. So that's the inverse relation. So what I've got in black here is actually in blue over here on this in the GeoGebra applet, and in red is in red over there. So that's we're going to solve that. Now when we solve this for y, is in the exponent, so y is a logarithm. So the way we solve this is we subtract a from both sides of the equation. So that eliminates the a on the right. And we divide both sides of the equation by c. And that's going to cancel the c's out. So we have e to the ky equals x minus a over c. Now we take this and rewrite it in a logarithmic form. The ky is the power, it is the logarithm. That's a ln, which is a log base e, of what's on the other side, x minus a over c. And then just divide by k. So y is 1 over k times ln of x minus a over c, like that. And so if this original function is f of x, then this new function is f inverse of x. Remember, this is not a power -1. It is what we just did here. Switch x and y and solve for y. So it's the opposite steps in the opposite order. And of course, graphically, we can see that as a reflection over this line y equals x, which is what this dotted line is right here. Okay? Over here, if you look in the table, you can see the formula for where we are. Here's the formula, y equals the blue, 1 times e to the 0.69x, that's the blue graph. And the red graph is y equals 1 over 0.69 times x to the times the natural log of x over 1. Here are some x and y values. These are actually controlled by these points here. If you want different ones, you can type in new numbers here in these black numbers, and those will be the x's for the exponential and the y's for the logarithmic. And we can see these swaps. So for example, here we have some of these points, and you'll see these points highlighted on the graphs. So you see 0, 1 is here because well, this is basically just y equals 2 to the x is what we have right now. So 2 to the 0 is 1, 2 to the 1 is 2, so you get 1, 2, then 2, 4, and so forth. Well, just as you get 1, 2 on this one here, we're going to get 2, 1 on the inverse here. 2, 4, the image point is 4, 2. Up here somewhere is 3, 8. Over here we have 8, 3. Here we have -1 1/2. Here we have a half -1. Here we have -2 1/4. Here we have 1/4 -2. This is -3 1/8, and this is 1/8 negative 3. Of course, these are rounded off to 2 decimal places, so obviously they're, like for example, this should be 0.125 instead of 0.13, but it's basically the same. Now, so we can look up and down here if we need to see that. Okay, to get to the sliders, unfortunately, I'm going to have to move this over a little bit, so we can't see the full detail there, but there we go. So there are the sliders. And so now we're going to experiment with this and see what happens as we change some things. So first I'm going to leave C alone and just change A and just change K, leave C and A alone. So notice what happens here. The bigger K is sort of the faster, the longer and tighter it holds the axis there, and then the faster it grows for the exponential, and the slower it grows for the logarithmic. Okay? At some point, there's a place here where they actually are going to actually cross over each other. Right now they're both on completely independent sides of y equals x, but at some point there are some values where y equals x on one or both, actually on both, right there. So they cross a couple of times, and we go on down here. Now, if you ever get to k equals 0, okay, there we go. Now you actually get a completely horizontal line for one and a completely vertical line for the other. Okay, so just y equals 1 in this case, or x equals 1 in the inverse case. So that's not really an exponential. That one we don't really count that one. So a negative k is going to end up now having the function kind of flips over, and so that it's decaying. Okay, so notice when you have positive k, look what happens. You've got a, let's move this over a little bit. I just used the right arrow, clicked out here and here, and used the right or left arrows to kind of move that. I think I can move it up and down as well, similarly. Okay, so let's see what happens. When the k is positive, notice that you're above the asymptote here, and it has the asymptote on the left, and we're increasing concave up for the exponential. The logarithm now is increasing concave down, and it's to the right of its vertical asymptote. When we go to k is negative, notice that we're above the x-axis, above the asymptote for the exponential, and still to the right of the asymptote on the on the logarithm. But notice on the logarithm, okay, let's look at where the asymptote goes. When the k is bigger than 1, this is above the horizontal asymptote. It's out on the left, and whereas we're to the right of the asymptote, but it's pointing down here on the red one on the logarithm. When we get into a negative k, hard time, it's not wanting me to select it here. I may have to restart this. I'm not sure what's happening. Alright, so allow me to move that one. There we go. Alright, now I can move it. Let's see if we can get the C back to 1 for now. Okay, and there we go. Alright, now it's allowing me to move, maybe. There we go. Alright, so now I'm over here for negative k. Notice that the asymptote is pointing up, or the graph is pointing up as it approaches the asymptote for the logarithm, and it's pointing to the right for the exponential. So in this case, they're both decreasing functions here. Now look what happens when I change the value of So let's go back to something like this. Change the value of A. Changing the value of A changes the value of that asymptote. So when you see the asymptotes as dotted lines there, so now A is about 1.5, and so now you see that x equals 1.5 is the vertical asymptote right here. That's this vertical dashed line for the logarithm, and y equals 1.5 is the horizontal asymptote for the exponential. So the first thing to notice here is these are just mirror images of each other over this line y equals x. So they have the same shape in a sense, and they're congruent shapes. They're just reflected images of each other. So if you just encountered one of these, they look basically the same in some sense. But how do you know if it's logarithm or exponential? Well, the logarithm will always have a vertical asymptote, and the exponential will always have a horizontal asymptote. So first of all, decide where the asymptote is, and you'll not only identify this value of c, but you'll identify whether it's logarithmic, the red one, or exponential, the blue one. Okay, and I've still got key points kind of identified here with where they just switch the x and y, so you can see pre-image and image. So notice if the c is positive or negative, we'll get to the c in a minute. A is just simply the asymptotes, so it's going to move those around. So you can have a positive or a negative asymptote. It doesn't make a whole lot of difference. Now, the C, so that's just a shift, vertical shift, or vertical shift in the case of the blue one, horizontal shift in case of the red one. So changing A is going to be a horizontal shift for the logarithm, a vertical shift for the exponential. Okay, the C is going to change how fast this thing is growing. Well, actually it changes, the percentage rate growth is the same. That's going to be affected by K. C is going to actually affect the stretch. So you can think of this as stretching out. So for example, if we can make C 2, for example, okay, there we go. So we're twice as far from the asymptote. Okay, so normally we would have been here 1 above the asymptote when x was 0. Now we're 2 above the asymptote up here at 0, 3, because now the asymptote is 1 in both cases. And so it has to do with how far this blue one has been vertically stretched. Well, if you stretch the blue one vertically, you're stretching the red one horizontally. It also turns out you can think of C as a horizontal shift. If you think of it that way, then the red one is going to be done with a vertical shift when we do C. Not by 2. 2 is more appropriately thought of as the expansion or compression factor. Okay, but it is you could think of it as a horizontal shift in the blue or a vertical shift in the red by the natural log of this, natural log of C. Okay. Now, if C is negative, it's flipped over. So let's look at C as positive. If C is positive, notice the blue graph is always above the line y equals A, the asymptote. It doesn't matter whether K is positive or negative, the blue one is still above that line. See that? And it doesn't matter whether that line is positive or negative, the blue one is still above the line. Well, what about the red one? The red one is to the right of its vertical line. Right, of its vertical asymptote, regardless of what K is. Now, if the C is negative, then it flips over, okay, and notice that the blue one now is always below that horizontal asymptote, and the red one is always to the left of the vertical asymptote. So the logarithm is to the left of the asymptote when you have a negative C, and when you have a positive C, it's to the right. Positive C, the red one's to the right. Negative C, that's to the left. Blue one, the exponential. The exponential is always below the horizontal asymptote with the positive C, below the asymptote with the negative C. So I think we've kind of seen most of the basic characteristics there, and I actually summarize a lot of these down here below. Okay, so some key observations. Any pair of inverse relations, the two graphs are mirror images of each other over the line y equals x, which is given a dotted line up there just for reference. And so these two shapes are congruent, reflected images of each other over that line. Both of these functions are continuous in one-to-one. That's pretty important. And regardless of what the a, c, or k were, they're continuous in one-to-one. The formula for the exponential can be written in at least three good ways. Y equals a plus c times e to the kx. That's the main form we were using. But e to the k is b, so we could replace e to the k by b here and write it as y equals a plus c times b to the x. Okay. And then the base is 1 plus the periodic rate, so you could rewrite the base as 1 plus r. And so depending on what kind of real-world applications we have, we might know r, or we might know b, or we might know k. But if we really know any one of the three, we can find the others. Well, how do you do that? Here are the relationships. B is 1 plus r, so solve for r, that's r is b minus 1. Okay, e to the k power is b, so solving for k, k is the natural logarithm of b. Now the inverse, is a logarithm function, logarithmic function. So these up here are for the exponential function. These relationships are just among these parameters, b, k, and r, regardless of which way we're writing them, exponential or logarithm. And here's the logarithmic form. Here's the basic one, which I saw for you a few minutes ago. Y equals 1 over k times natural log of x minus a over c. But I can replace this as k is as you see, is the log of b. Okay, so we could actually rewrite this. Let me go down here. We could rewrite this as y equals natural log of x minus a over c over k. But k is the natural log of the base, b. And our change of base formula allows us to rewrite this as log base b of the x minus a over c. So we could write it that way if we'd rather. So another way to write it, which is what I have right here. That means log base b. Talk about some x and y intercepts. Well, the exponential function will always have a y-intercept, but it doesn't necessarily have an a-intercept. It depends on the vertical shift. So if there's no vertical shift, it's not going to touch the axis. So basically, it doesn't cross the asymptote ever. So if the a is a negative number, well, this is not exactly right. It says it's an x-intercept is natural log of negative a over c divided by k, comma 0. This is true if the minus a over c is positive. So the minus a over c has to be positive. So, for example, if a is negative and c is positive, then there's no then this will work, for example. Or if a is positive and c is negative, that'll work. But if they're both positive or both negative, then it's not going to work. Okay. So that sometimes happens, sometimes doesn't. It's exponential if it's exponential, the y-intercept, it does have one, and when x is 0, y is a plus c. And similarly, the exponential always has a y-intercept. The logarithm always has an x-intercept, which is just the reversed, a plus c, comma 0. And again, just reverse the exponential one here to get the logarithm one reverse the x-intercept to get the y-intercept for the logarithm. And again, the same restrictions I said a while ago. A times c, or a and c have to have the opposite sign. So a times c has to be negative. I'll rephrase that and maybe repost this. The exponential function always approaches a horizontal asymptote where y equals a, which is shown dashed, and it only happens on one end. The logarithmic function always approaches a vertical asymptote of x equals a, which is also shown as a vertical dashed line. If the graph is given, then you could identify the asymptote to determine if it's exponential or logarithmic. We talked about that. The domain of the exponential function is a set of all real numbers, because we can raise a positive base to any real number power. But notice we cannot take the logarithm of a negative or a zero power. So the thing we're taking the logarithm of can't be a negative. Okay. So if c is positive, then the graph of the logarithmic function is entirely to the right of the vertical asymptote. The domain is the x is greater than that a. And if c is negative, the graph of the logarithm is completely to the left of the vertical asymptote, and the domain is x is less than a. Of course, if c equals 0, then it degenerates just down to a line. Now, if we look at the range, if the c is positive, then the graph of the exponential is entirely above the horizontal asymptote, and the range is y greater than a. And if c is less than 0, the graph of the exponential is entirely below the horizontal asymptote. Okay, so that gives you a range of y less than a. But the range of the logarithmic function is always a set of all real numbers. So that tells you something about the domain and range. What's the effect of changing c? We saw that the value of the absolute value of c can be thought of as either a strain of an expansion or compression by a factor of c, absolute value c, or it can be thought of as affecting a translation, a distance of natural log of the absolute value of c. So it's a vertical strain and horizontal translation for exponential functions. It's a horizontal strain and vertical translation for logarithmic functions. The effect of changing k is the continuous rate of growth if it's positive, or decay if it's negative, in the basic exponential function. So if k is positive, k is always positive when r is positive, when b is greater than 1. That's your basic exponential growth function, at least for the basic one. Okay, and no matter what, it's going to approach the horizontal asymptote on the far left for the exponential function, and the graph of the logarithm will be pointing down as it approaches its vertical asymptote. On the other hand, when k is negative, that'll happen exactly when r is between -1 and 0, so r is negative also, and the base is between 0 and 1, so you got a small base when you got a negative k. And in this case, the graph of the exponential will approach the horizontal asymptote on the far right. In your basic exponential function, that's going to be your exponential decay function. But in general, even after we translate it and transform it and all that, you're always going to be approaching the asymptote on the far right in that case. Whereas if it's a logarithmic function, it'll be pointing up towards its vertical asymptote. Okay? And so that summarizes some of the things that we noticed when we looked at this. So I encourage you strongly to open this yourself, experiment with this, and try it out with some different examples.